Good morning, everyone, and very welcome to the 2022 Symposium in Mathematics, Number Theory. My name is Dan Larhammar, and I'm the president of the Royal Swedish Academy of Sciences. I'm delighted to see all of you here to celebrate the 2020 Crafoord Prize and Crafoord Laureate, Professor Enrico Bombieri. Before we enter the world of mathematics, let me tell you a little bit about the background of the prize and how it all started, the very reason why we can all be here today and enjoy science and research at the highest possible level. The founder of the prize, Holger Crafoord, was a Swedish industrialist. He graduated from the Stockholm School of Economics, and in the 1940s, he worked for a company here in Lund, Åkerlund and Rausing, that manufactured packages. Holger Crafoord served as the managing director for the company from 1946 and onwards for more than 20 years. This company formed a subsidiary already in 1951 that was named Tetra Pak, which became a huge success with a very clever design of packages for beverages like milk and juice in the shape of a tetrahedron with a plastic cover on the inside. The success of the company meant that Holger Crafoord, when he sold his shares, he made a considerable profit. Somewhat later, he was approached by a medical researcher and inventor and professor of medicine who was devoted to improving the situation for his kidney patients. This researcher, Nils Alvall, had invented an artificial kidney a few years earlier, and this was designed to purify the blood by dialysis. Holger Crafoord then founded the company called Gambro here in Lund in 1964 to develop and manufacture these instruments, and production started in 1967. This dialysis instrument and its followers have extended the lifespan and reduced the suffering for literally millions of kidney patients over the years. So Gambro too was a great success and went on to improve other things in medicine. It became an international company, and since 10 years it is owned by Baxter in Illinois. The success of Gambro as well made it possible for Holger Crafoord to set up a foundation for research in 1980. And this foundation awards science prizes, as we all know, in areas of research that are not covered by the Nobel Prizes. In addition to mathematics and astronomy, also in the geosciences and in the biosciences, especially ecology, and also in polyarthritis. And this is because Holger Crafoord himself suffered very badly from rheumatoid arthritis during the later years of his life. The prizes are awarded in a 4-year cycle, and the first prize was awarded in 1982, so it is a 40-year jubilee this year. Then let me just add a few words about the selection process for the laureates. This is handled by the Academy of Sciences, and we receive over 100 nominations each year. We have an extremely careful selection process with a prize committee, very similar to the Nobel Prizes, and the decision is taken in the Academy as a whole. This is one of several important tasks for the Academy, all of which aim to promote the sciences and strengthen their influence in society. Another way to do this is to provide meeting opportunities for scientists like we are doing here today. In 2020, the Crafoord Prize was awarded in astronomy and mathematics, so finally the prize ceremony and the corresponding symposium are taking place this year. So I will now give the word to Per Salberger, who is a member of the Royal Swedish Academy of Sciences, who will present the Crafoord Laureate. Please.
So I will be very brief because I gave a longer presentation yesterday and there will be another one tomorrow. But let me just say that this has now, as was already said, this is 40 years past since we were the first prize. But this is the first time we have a symposium in number theory. And this is very much thanks to 175 publications with 3,400 citations by Enrico Bombieri. But I would like to stress that all his publications are not in number theory. So in the 60s and 70s, he also solved very hard problems in analysis, geometry, and he even solved a problem about classification of finite simple groups that the group theories couldn't solve. So he's not just a number theory, but today we will have number theory. And if you look at Bombieri's papers in number theory, you can divide them into two categories. So one class of papers is then in analytic number theory, especially then distribution of primes, and Bombieri, he developed a sieve theory. And we will now have two great experts today. World-leading expert, we will have James Maynard before lunch, and at the end we will have Henrik Ivanic. And then there is Bombieri's work also he has also made very important work in Diophantine geometry, and for that we have two excellent speakers as well. It's Marc Andry and Jonathan Pila. And then we will have Fabien Pasuki as chairman. So I think that was all I wanted to say. So now I will give the word to Per.
Thank you. It is a great pleasure and honor to introduce Professor Enrico Bombieri from the Institute for Advanced Studies in Princeton, the winner of the 2020 Crafoord Prize in Mathematics. So Professor Bombieri is an extraordinary mathematician known for his depth, exceptional depth as well as breadth. He's perhaps most well known, this could depend on whom you ask, but in my book I'd say he's the most known for his work on prime numbers, in particular what is known as Bombieri's theorem, which tells us that the generalized Riemann hypothesis holds on average. And here I should add that I think the generalized Riemann hypothesis is the most important unsolved conjecture in all of mathematics. And what is remarkable is that Bombieri's theorem is often, not always, but often just as good as knowing the full generalized Riemann hypothesis. And he's also worked in many other areas. I think Per covered them quite well, so I'll skip to a brief summary of his many laudations. He received the Fields Medal in 1974, the Balsan Natural Science Prize in 1980, the King Faisal Science Prize in 2010, and now also the Crafoord Prize. So please.
The title of this lecture is Learning from Trying. Trying is a very forming experience. You know, when a postdoc student comes to me and asks, what should I do? And ask, what do you think you want to do? Say, I want to write my thesis for publication. And I say, no. You're here at the Institute to learn new things. Where in the summer, when everybody leaves, you have nothing else to do, then you work on your thesis. And sometimes I'm a little tough with them. And so I ask them to report on a regular basis and check that they don't get lost. The Institute is a very intimidating place because, you know, the ghost of Einstein is everywhere. So, just a second. anyway, to make students comfortable is one of our job, for this postdoc. And one of my best students has been Jonathan Pilla. And again, when he came, I asked, what do you want to do? Oh, I want to write my thesis for publication. I said, no, you're here to learn new things. And he did, and he's one of my very, very best students. And now I'm learning from him. So it's fantastic what he did, and very honored that I had him as one of my postdoc students. And so I have very good memories, in fact, also from Sweden, where with Lennart Carlsson we put together a program in the summer about this time, in fact, for postdocs to come here with students and again have advanced seminars at all levels, various levels. And so they will not get lost in the summer, have the beautiful surroundings of Lund, and the thing worked very, very well. So my memories here are really great, and I'm very honored to be here and surprised in many ways. And old memories come back, and I was even able to talk to Lennart Carlsson, who is now retired and has become totally blind, and we talked a bit and recalled the good old times. And again, that was a very emotional experience. So, to me, Sweden is a very special place, and especially here, and being back is a lot of very nice memories. Come back, everything very pleasant and very beautiful. So thank you for having this occasion to be here again, and this time as a surprising as a recipient of a prize instead of handing out the prize. And so now it's time to say a few things about the actual title. And the subtitle is Learning from Trying. Learning does not consist only, well, here is the book of so-and-so, it's a good introductory book, you read it, if you have problems, come to me, I will clarify it. Learning also is trying. And if you try too early, you get lost. If you don't try, you never go forward. So it's a very delicate thing, and not everyone responds in the same way. So postdocs have to be followed not just by results on tests, but by sometimes the programs have to be adjusted to the capabilities of the postdoc. So in Sweden, my experience has been that the programs are not too big, and so very adjusted, and the results is very good for Swedish mathematics. So next I should say a few things about the actual lecture. Learning from trying. Learning is a continuous process, and here we go. Here we have what I consider the founding fathers of number theory, Euler. Extremely interesting to read even today. Well, they have to know a little Latin, perhaps, but I did the classic studies, and that was not a problem. Then Dirichlet and Riemann. Those are the three great founders of modern number theory for the study of prime numbers. So Euler is the one who introduced the zeta function. In fact, he used also alternating signs because then the series becomes convergent. And he discovered, in fact, in a form equivalent, the functional equation, the famous functional equation of the zeta function, the Euler product, the relation prime numbers, written here in modern form. Euler studied with alternating signs because he wanted the sums to be convergent. Anyway, Dirichlet was the next great progress, studying distribution of numbers in arithmetic progressions. So numbers, say, that divided by 4 remainder 1, or possibly remainder 3, and so on, and introduced techniques of group theory. And he proved the first really very new deep theorem about prime numbers, that arithmetic progressions without fixed divisor contain infinitely many primes. There was one obstacle to that, and he solved that obstacle when he was in Rome, in the Sistine Chapel, for the Easter celebrations. He had the intuition how to show that something was not equal to 0, and that was for him kind of a miracle. Riemann, 1859, showed how to relate primes to with the zeta function as a function of a complex variable. Euler studied it with something equivalent as a function of a real variable, but Riemann understood the intuition that going into the complex numbers he could go. And then he was able to produce a formula, exact formula for counting prime numbers by analytical methods. So this was a great achievement. Basically, the beginning of what is called today analytic number theory. The Riemann hypothesis is, I consider, is the biggest unsolved problem in number theory. Is that the so-called zeta function, all the when it vanishes, it vanishes -2, -4, -6, and so on. Those are the easy ones to compute. And then there are complex numbers. And Riemann had numerical calculations of them and discovered that all these complex numbers have real part exactly equal to 1/2. And there is a nice story that the mathematician Siegel and Weil went to see to Göttingen and wanted to look at Riemann's notebook. the university provided the original notebook, and the story is quite amusing. Was just a block of loose papers, sheets, handwritten, and some fell down. They're full of numerical calculations. Now, Hilbert thought Riemann, of course, he was one of the greatest mathematicians of all times, and always said that Riemann was working by miraculous intuition and so on. And when the notebook arrived, these papers fell on the floor. Siegel picked one and showed this calculation, numerical calculations all over and so on, and showed to Weil and said, well, here what Hilbert said are the great abstract, is the great abstract thinking of Riemann. So, again, we create our own idols, but reality is more complex than that. And sometimes you reach maybe the level of becoming idol by doing what Riemann did. Hard calculations and thinking, deducing, and then that gives the support for deep ideas. So, I mentioned that Riemann noticed that pi of x, the number of primes up to x, is less than the function, the logarithmic integral of x, for x up to 3 million. And this is remarkable. Then this persists for all x up to 10 to the 23. That's a very big number. But now the first sign change is around 1.4 times 10 to 316. It's kind of amazing that this regularity goes up to such numbers, gigantic number, and which has some specific meaning. I think it's the largest number ever which has a specific meaning in number theory. And but it's known that pi of x infinitely often is larger than LIX and infinitely less than that. So usually pi of x is less than Li of x. The probability that happen is almost 100%, but not quite, just a tiny bit less. So, about myself, I can say I read the Hardy and Wright's book, 1955, so I was 14 years old. Introduction to the Theory on Numbers. My father bought the book because he saw it in London in a bookstore, and then found it difficult. I already was interested a bit in mathematics, and quickly I took the book, and it was my introduction. My father said, maybe I should consult my colleagues in the Banca Commerciale and about my interest in mathematics. And it turns out one of his colleagues, his daughter, was studying mathematics with Ricci, Professor Ricci, and said, it's fantastic. So a meeting with Ricci, he took me under his protection, told me what to do. So continue to study Latin and Greek, the classics, and come to me, correspond, and once in a while he came to Milan, because I was living in Tuscany, and my father was working in Milan, and come and we talk. And then in '64, big change. 10 minutes lecture in Oberwolfach, and Davenport immediately invited me to go to Cambridge. So the year in Cambridge was the opening in new directions. And then after that, a meeting with Serre, Jean-Pierre Serre. And then '65 was the real turning point when Davenport came to Milan. And the story is quite amusing. And Davenport said at the end of our visit, well, now we have to write a paper together. And I said, do you have any suggestions? I have a list of 20 problems. So we went through the list of 20 problems, and they said, which one do you like? I said, I don't like any of them. And he said, what do you suggest? Well, I have these things about prime numbers and so on. And essentially, he said, oh, that's new. And that became the large sieve paper, which really introduced me to the higher world of mathematics. So, again, '65, I was interested in all of mathematics, algebraic geometry, and so on. '66, military service, very instructive, because I met the segment of society which was a sample of all of Italy. Low level, high level, good, bad, and it was very interesting. We are still in touch with each other, the 44 students at officer school. And '69, partial differential equations, the Giorgi, everybody knows his name, Stampacchia, also a great mathematician. And so the 65 was the result of the visit with Davenport, and here is the formula, which has become quite standard by now and allows to study prime numbers in progressions, not one by one, but all at the same time. So the consequence is the so-called prime number theorem for progressions is true on average almost always. If there are deviations, they don't count too much. And so this result is as predicted by the so-called Riemann hypothesis, which is not proved in any single case. In the so-called function field case, it's proved. But in the classical case, it is still the deepest open problem in number theory. But on average, it is correct. So that was the theorem which was proved. How to find a proof? Well, I'll skip that. And the only thing, all sums were supposed to be over squares and so on. Now, usually when you study a sum in one variable, you study at the beginning, then continue step by step, study the whole sum. But summing two variables, you have a rectangle to explore. How do you explore it? And you have to divide in subrectangles, and then it becomes a little tricky. But it turns out is if you have a worst subrectangle, then everything else is estimated in terms of the worst possibility, and on average you can say something, and suddenly you get very unexpected results. So I will. So how this came out? Well, Davenport was visiting, and said the Wednesday morning, on the end of his visit, Davenport said, "I have a list of 20 problems to look at. Let's choose one to work together for a joint paper to end this nice visit." So I went through a list, and which one do you like? And I said, well, I don't like any of them. And it was not because of disrespect, because I really didn't like these problems. And said, what do you suggest? So I have some notes on prime gaps, and then Davenport looked at that, and then wrote a paper on prime gaps. And that was the basically the start of the so-called, today it's called the large sieve, which has become a basic instrument in number theory. And I worked, Davenport went with his wife to Venice for 3 days, met him then at the railway station. He would never fly on a plane. And when he was going back to England, and worked 2 days and 3 nights non-stop, and gave him the manuscript on the large sieve to him, and said, "I think you would like to read this." And that was the start. So then he continued, and then somehow Davenport talked to his friends, and Serre in Paris got interested, and he became after Davenport, my second personal teacher. And I'm still extremely grateful to him to learn, not just, I was absorbing mathematics really non-stop. I loved that. So this, I skipped that. And Cambridge, learning on the job, not just by reading books. So you read books, but also you try. And Davenport wanted to study new work by Dwork on zeta functions over finite fields, whatever they are. And so I knew the classical theory, functions of a complex variable, entire functions, meromorphic functions, and so on. And I realized that why complex numbers? On p-adic numbers, p-adic analysis, you can have the same concepts. So I used what I knew of complex function theory and transferred these ideas to p-adic analysis, functions on p-adic fields, and the analog of complex functions. And suddenly an entire new area of mathematics was open to me, and to others too. So I gave a lecture. And then there was a short guy, not this tall, now shrunk a bit, but he was quite a bit. And he was looking at me like this and said, "Are you a student at work?" after my presentation. I said, "No, I'm a student in Davenport." But Davenport does not know these things. Yes, so he asked me to read Dwork's paper. I read it and transferred method of complex function theory, with which I was very familiar, to the p-adic function theory, and solved my problem. Then he told the next speaker, the organizer, I will attend the next lecture. And to me, he said, I'm Jean-Pierre Serre. Let's take a walk in the woods. Then he learned everything about me. And then 2 months later, we see a letter from the USA State Department, invitation, summer school in Woods Hole, geometry and topology, special visa, allowed me to travel free everywhere I wanted in the United States for 6 months. And this I did, not just for vacation, also visiting universities, attending meetings, and so on. And so this was really turning point. I found all the doors open. And I enjoyed doing that. So I became a mathematician full-time. So what are zeta and L functions? They're a zoo, really, maybe. And they're not isolated objects. They're all fused together. And we're still trying to understand them. I spent all my mathematical life trying to get a little bit more, a little more. And we got some relations with the Laplacian in L2 space and so on. And work never ends. It's a beautiful area of mathematics, still making progress. Jonathan Pille has contributed in his own way to development these things. Now he's a big shot, and I consider him one of my students. Well, thank you. And progress or conjectures? We don't know. And the usual conjecture, well, things oscillate and so on, is a double log distribution. No, apparently for the Möbius function, the oscillation triple log to the power 5/4. Why? We don't understand. But there is evidence. So standard random probability theory does not apply to prime numbers. It's a different kind of thing which belongs to the future to understand why. So there's a lot more to do in the future, a lot of new directions, the fusion of different branches of mathematics, our probability theory, the set theory in high dimension, by the way, the study of orthogonal functions in more than one variable, which in Sweden has become very, very important in combinatorics. Now is taking use in number theory. So it's beautiful to see all these developments. I cannot really follow all of them, but I can watch the progress being done, and I think the mathematics goes forward. Thank you.